Okay, so 7 to 8%. 7 to 8% of every single ton of CO2 that humans put into the atmosphere every year comes from making cement.
Just cement. Not steel, not planes, not cars, cement.
And the wild thing is, cement plants are also just hemorrhaging heat. Like 30 to 40% of their thermal output just gets thrown away.
Thrown away into the air, gone, and I'm Brian.
I'm Rachel, and we are about to get extremely nerdy about.
I'm John. And this is the part where Brian pretends he understood the electrochemistry before I explained it to him.
I understood most of it. Welcome to KPsphere Signals.
So the actual thing we're talking about today is this concept of a battery, a very specific kind of battery that could do 3 jobs simultaneously.
3 jobs, which is already suspicious, right? Like when something claims to do 3 things at once, it usually does none of them well.
Except. The components here have all independently crossed into legitimacy. That's what makes this interesting.
Right, so break it down. You've got 3 technologies that are each real, each proven-ish, and nobody has bolted them together yet.
Okay, so here's the setup. And this is where it gets actually kind of crazy. The first piece is something called a thermally regenerative electrochemical cycle, TREC, which sounds like a transformer, but is actually more interesting.
It's way more interesting than a transformer. I said it.
You did not say that before we started recording.
I thought it very loudly.
So a TREC. The basic idea is that some batteries change their voltage depending on temperature. And if you're clever about it, you can discharge the battery when it's cold, then heat it up, and it will actually recharge itself using only the heat.
Which is wild, because normally we think of charging a battery as, plugging it in. Electricity in, electricity stored.
Right? But here you're converting heat directly into electrochemical work. No turbine, no steam cycle, no generator in between.
And the heat doesn't even have to be that hot. We're talking below 120 degrees Celsius. That is barely above the temperature of really aggressive coffee.
That's the temperature of industrial waste heat that currently does literally nothing.
Which every cement plant has in enormous quantities, just venting off into the sky.
2,400,000,000 tons of CO2 a year from cement. 30 to 40% of their heat just wasted. This is a crime.
It's not a crime, Brian.
It should be adjacent to a crime.
I mean, it's definitely a missed opportunity worth tens of billions of dollars, which in some jurisdictions.
Thank you, John.
Okay, so walk me through the second piece. Because TREC is interesting, but it's not new. What's the vanadium thing?
Okay, so vanadium redox, flow batteries, VRFBs. These are already a real commercial technology. Sumitomo in Japan is deploying them. Company called Invinity, Ronke Power in China. These are grid-scale storage systems. They already exist.
The cool thing about vanadium flow batteries is that the energy is stored in liquid, in tanks of electrolyte, so you can just make the tanks bigger to store more energy. It scales.
And they last a very long time, relatively speaking. We're talking over 15,000 charge cycles.
Your lithium-ion phone battery is over here crying right now.
Actually weeping. Deeply personal.
The knock on vanadium flow batteries has always been cost. We're looking at $300 to $500 per kilowatt hour. And that's driven by vanadium prices being volatile and membrane costs being high.
Which is real. That cost problem is real. But here's the thing. If the battery is also doing 2 other jobs for you, that cost amortizes differently.
Which brings us to job number 3. And this is the one that I genuinely did not see coming.
The CO2 capture.
Right. And this is where it gets crazy. There's a whole subfield called electroswing CO2 capture. MIT spun out a company called Verdox based on this. The idea is you use redox active molecules, specifically quinones, that chemically grab CO2 when they're in a reduced state and then release it when they're oxidized.
So the same electrochemical infrastructure that's storing energy could also be doing gas separation. At the same time,
One system, one capital expenditure, 3 functions.
Battery charging, carbon capture, and heat to electricity conversion, all happening in what is essentially a very sophisticated tank of liquid.
I love this. This is like if your refrigerator also generated power and cleaned the air while keeping your leftovers cold.
That's actually not a terrible analogy.
It's a slightly terrible analogy, but the spirit is right.
I'll take slightly terrible.
So what are the actual efficiency numbers here? Because I want to stress test this a little.
In lab settings, and this is important, lab settings, the TREC component has demonstrated 5 to 7% Carnot equivalent conversion efficiency.
5 to 7% sounds low.
It sounds low.
Okay, but here's the context. Carnot equivalent means relative to the theoretical maximum. And for heat below 120 Celsius, the theoretical maximum is already pretty modest. You're extracting work from heat that literally had zero value before. 5 to 7% of something beats 100% of nothing.
Fair. That's actually fair.
And when you couple the vanadium system to CO2 active species, the carbonate and bicarbonate chemistry, the effective temperature coefficient can exceed 1.5 millivolts per Kelvin in those hybrid configurations, which is genuinely good for this class of system.
How do you know what millivolts per Kelvin means?
I read things, Rachel. I read things.
He definitely Googled it in the green room.
I did not. Okay, I did, but it stuck.
So what are the actual hard problems? Because this seems like the kind of thing where if it were easy, someone would have done it.
Great question. And yes, there are real blockers. The biggest one is membranes.
The membranes. Tell them about the membranes.
So inside a flow battery, you have this membrane that separates the two electrolytes, anion exchange membranes, and they work fine in a normal vanadium battery. They work fine in a CO2 capture system, but run them in both environments simultaneously and they degrade 2 to 3 times faster.
Because you're hitting them with vanadium crossover and CO2 saturated conditions at the same time.
Exactly. And that's a real engineering problem. That's not a write more grant proposals problem. That is a materials science problem that requires actual breakthroughs.
Which is either exciting or terrifying depending on your disposition.
It's both. It's both at the same time.
Kinda terrifying, actually.
See, he always gets there eventually.
Okay, so let's talk about where the money is. Because the funding picture here is genuinely weird.
Okay, this is the part that I find almost offensive. The constituent technologies, vanadium batteries, electro-swing capture, trig chemistry, have collectively attracted over $2.1 billion in R&D investments since 2020.
2.1 billion.
But specifically integrated cement-coupled hybrid systems? The thing we're actually talking about? Under 80 million in identifiable funding.
So the gap between the pieces exist and someone put the pieces together is like a $2 billion blind spot.
That gap is the prize. Whoever integrates this first sets the technical standard. They capture the IP. They become the reference implementation.
And they get to be very smug about it at conferences.
Who's doing the foundational research right now? Like, which institutions?
University of Notre Dame got 1.2 million. University of Maryland got 550K. Stevens Institute has 545K. There's work happening at Brown, UT Dallas. It's distributed. It's university-led. It has not consolidated into a company yet.
Which means the commercialization window's open, like wide open.
And then on the corporate side?
Holcim, Heidelberg Materials, Cemex, the 3 biggest cement companies in the world, have collectively committed over $5 billion in decarbonization capex through 2030.
$5 billion looking for solutions. And the specific solution we're describing has under 80 million in research funding.
That mismatch is insane.
The other thing that's happening is the policy environment just got really aggressive. EU Carbon Border Adjustment Mechanism, CBAM, went into full enforcement in 2026. And in the US, the 45Q tax credit now pays $85 per ton for sequestered CO2.
$85 a ton. And cement plants produce massive amounts of CO2. Do the math.
If you're capturing a meaningful fraction of a cement plant's emissions and getting $85 per ton for sequestered CO2, the carbon credits alone start to change the economics.
And that's before you count the value of the grid storage or the heat utilization. The whole pitch is that CBM plus 45Q plus avoided energy cost might actually make the stack cash flow positive at industrial scale.
Might, important word.
Might. We're not there yet. But the trajectory is, look, the grid scale long duration storage market is projected to reach $50 to $70 billion annually by 2030. That is a massive gravitational pull.
Okay, but here's my pushback. And I want to push back because I think it matters. What's the competing pathway? What else is cement trying to do?
Great question. You've got a mine-based capture, which is proven but energy intensive and kind of gross chemically. Calcium looping, which works but needs high-grade heat, which defeats the whole low-grade heat pitch. Electrified kilns, which require enormous amounts of green electricity that doesn't exist yet at scale.
And this is where the window comes in, because cement companies are making CapEx decisions now. In the next 24 to 36 months, whatever gets to demonstration scale first is probably going to lock in the standard.
So this is actually a race.
It's absolutely a race. And the finish line is a working pilot at industrial scale, not a lab demo. An actual cement plant with this thing bolted onto it, producing data.
The TRL levels are telling here. VRFBs are at TRL 8 to 9. That's commercial deployment. Electroswing CO2 capture is TRL 5 to 6. Verdox has pushed it there. TREC chemistry is earlier stage. So the integration is the hard part, not the individual pieces.
Which means the risk isn't, does the science work? The risk is, can you make three mature-ish things cooperate in one physical system under real industrial conditions?
Which is actually a more tractable problem than fundamental science uncertainty. It's hard, but it's engineering hard, not discovery hard.
Engineering hard is the kind of hard that responds to money and good teams.
As opposed to physics hard, which sometimes just doesn't.
As opposed to the universe said no hard.
The universe has said no to me many times. This is different.
Okay, let's talk about the geographic angle, because I thought the research distribution was interesting.
So the US is leading on foundational research, about 40% of the identifiable work. China is in there at 5%, South Korea 3%, Australia 2%. But there's a huge chunk, 45%, that's essentially unattributed or multinational.
Which means either someone is working quietly and not publishing, or there's a bunch of international collaboration that doesn't map cleanly to one country.
Or both.
China's got an interesting angle here because they have huge vanadium reserves, like strategically significant reserves, and they've been pushing VRFBs hard through Ronki Power. If they solve the integration problem first,
they could control the vanadium supply and the technology. That's a very uncomfortable position for everyone else.
It's kind of a rare earth situation, but for batteries.
Yeah, and cement is a completely local industry. You build plants near the demand. But the battery technology could come from anywhere. So whoever owns the IP wins regardless of where the cement plant is.
There's a patent landscape forming here too. There's already a USPTO filing on the electroswing approach, 2021 00387139, and a Canadian patent on acid gas capture and release. The IP race has already started.
Okay, so hot take time. I'll go first. I think this is real, but the 24 to 36 month window is actually generous. I think it's tighter. Cement CapEx cycles are long, but the policy pressure from CBM is forcing decisions now.
I think the membrane problem is more serious than people are pricing in. I'd say you need 18 to 24 months of material science progress before you can even run a credible pilot, which means the window might actually close before the tech is ready.
I'm more optimistic. The convergence of mature components means a well-funded team could make real progress on the integration. It's expensive, but it's not impossible. I think you could see a real industrial pilot by 2028.
2028 is ambitious.
I'm an ambitious person.
If someone gave a crack team, say ex-Verdox people, some VRFB engineers, a good material science group, $100 million in 3 years, I think they get there. The question is, does that team exist, and does anyone write that check?
The check could come from Holcim or Heidelberg. They have the capex committed. They have the plants. They have the motivation.
They literally have the waste heat just sitting there, waiting.
The strategic framing here is that for a cement major, this isn't just a decarbonization project. It's a grid revenue stream. You're not just reducing your carbon liability, you're becoming a power storage asset.
A cement plant that also sells grid storage services and gets $85 a ton for sequestered carbon, if the economics work out. That's a completely different business model.
It's wild. It genuinely reframes what a cement plant could be.
From liability to asset, that's the pitch.
From the thing that's contributing heavily to climate emissions to, well, not doing that, and also potentially making money from not doing that.
That's a little reductive.
It's extremely reductive and also captures the spirit of it.
The bottom line is, the science is sound. The integration risk is real. The policy tailwinds are the strongest they've ever been, and nobody has done the full stack yet. That combination doesn't come around often.
High conviction, position selectively. That's the read.
Watch it closely. If you see a cement major announce a pilot partnership with anyone in the VRFB or electroswing space, that's the signal.
That's the moment where this goes from interesting research to the thing that changes how we think about industrial decarbonization.
And we will absolutely be losing our minds about it on this podcast when it happens.
Preemptive losing of minds right now, in advance.
The full research report on this, 177 sources, all the funding records, the patent landscape. It's up at KPsphere.com if you want to go deep on it.
Link in the show notes. It's worth your time.
This has been KPsphere Signals. I'm Brian, she's Rachel, he's John, and a cement plant somewhere is wasting an enormous amount of heat right now while we speak.
Go fix that. Someone, please.
We'll be back next week with something equally unhinged. See you then.